With this induction question, how many of you guys started step 2 and then what happened after that?
Step 2 what?
Step 3, sorry. Step 3. Where did we get stuck?
Well, we got, meaning it's got to the end, but like it just didn't match up.
Didn't work out, right?
Yeah.
And I guess the good thing about induction is that you can always know whether the answer's right or not. If you've done all the algebra properly, you should end up with what you're trying to prove, right? Let's take a step back and look at this question, because this question is actually slightly different to the induction questions. Because if you look at it, there's actually n's throughout this whole thing, right? There's n's throughout this whole thing. And what I like to do is I actually like to go back to numerical examples to understand a problem. Remember how I said like going back to just understanding what induction is trying to prove is very helpful? Have a look at this. What am I actually trying to prove here?
When you get a number, add 1 onto it each time until it gets to that number.
That's a great English definition of what we're doing. You start with some number, and you add all the numbers until you get to double that number. So, I mean, this is not a very interesting case. This is for n equals to 1, right? N equals to 1, you only go up to 1 plus 2. And that equals to 3. Okay, great. Not very interesting, right? N equals to 2, though, is a bit more interesting, because now what happens? Well, we go 2 plus 3 plus 4. Okay. And that's going to equal to 9, right? N equals to 3. We can keep going on for a bit. All right. Quick maths, 18. Right? So something interesting happens with this series summation, because each time, like when you're adding them, not only are we adding more digits there, but like what happens with the starting place? The starting place gets kind of shifted. Can you see that? Right? So that's something interesting to think about. Right? This is different to other induction questions because the series is kind of shifting along. So how is that going to change the way in which we prove that? Well, quite dramatically, actually. And that's why it's important to recognize what you're actually doing before you start the process. Because if you hadn't realized that this is happening, then you won't be able to actually prove by induction in step 3 that this is going to work. Let's just check that it works, by the way, right? So, always, our induction process, step 1. Test true for n equals to 1. So if we're testing true for n equals to 1 here, right, I think you guys found out that it didn't quite work out, right? Because what were you trying? Well, when you were putting LHS, what did you put as the left-hand side?
You said n equals to 1.
N equals to 1. And what was, when n equals to 1, what does this left-hand side equal to? Right, and this is the trick. This is the problem, right? Because we look at this and we usually just go straight back to this guy. And we say, okay, that's the whole left-hand side. But in actuality, like, what is this saying? It's saying I take n, add all the numbers up until 2n. So for LHS, right, I'm going 1 plus 2, which does equal to 3, right? So 1 plus 2, yeah, it does make sense. Not dollars. And then the right-hand side, we can test it as well. So we get 3, outside 2 on 2. Yep, that does equal to 3. Therefore, true for n equals to 1. Yeah. Jot that down for me. Step 2. Right, this is the fun one because we always know how to do this. Assume true for n equals to k. That's right. Well done, Harry. This is a fun one because I can always get it. Okay, now here's where we ran into, here's our roadblock, here's where we ran into trouble, right? Step 3, prove true for n equals to k plus 1. And it's important that we get this one right, because if you write down the proof requirement wrong, then you're never going to get to the right answer, right? So this time, can you see, oh, we're starting from k plus 1, which makes sense when we look at it numerically, we're starting from the one after, yeah? Okay, so that's kind of getting some intuition of what's going on here. And then each of these guys, I'm substituting n equals to k plus 1, so that's just going to be k plus 2, that's just going to be k plus 3.
That makes sense,
so. It does. I'm glad it makes sense to you, Harry. Then you can help me out. What am I going to get over here?
You know, some more stuff, you know.
2k plus 1.
Yeah.
And what does that equal to?
That equals to that one.
What?
3k plus 1.
Yeah.
Equals 2.
And then here, if you recognize, hang on, well, if you're just substituting n equals to k plus 1, that's just going to be k plus 2. All over 2. Are you with me so far?
With you, sir.
Good.
I got the end.
Now here's where it gets tricky, right? Because again, what's the problem? Well, the problem is that we always want to substitute in some way what we've proved, or assumed rather, in this step 2. We want to try and insert it into step 3 some way, right? And when you try and do that, when you start with the left-hand side and you have that, like, what's the problem that you run into?
It's not the same.
Well, what's not the same, Harry?
We can. We can.
Well, how can we do it?
Okay from the top.
So you want to like introduce a k, but then take it away again? Is that what you're suggesting?
So,
Yeah. Did I make a mistake?
you mean to change it from 2k plus 1 to 2k plus 2?
Yeah, let's do that. Let's just leave it like that. That's all right. Is that what you're saying?
In step 2,
Hmm.
minus that first k onto the other side.
Okay.
And then it fits in, you know?
So like that you're thinking.
You were right, right?
See, I'm not convinced with this. I'll tell you why. Because, like, where does it fit in? You need all the way up until 2k.
Yeah, it just fits slots in right for us.
So you're saying over here, like, where's the 2k over here?
Why doesn't it work like that?
Like, where's the 2k?
There's a 2k. 2k before
Why
it.
did you change it before?
The 2k before it.
Where? Here?
Yeah, but like you can just like.
Oh, you mean like this, right?
Yes.
Is that what you're saying?
Yes.
Okay. Now here's the trap. Here's the trap, right?
Yeah, so you're saying it's,
Sir's got a condescending tone, John's wrong.
it's 2k minus 1.
Got the red marker out.
You got my reads going on. Here's the problem with the mentality is that we're always shifting or adding an additional term. But why don't I start with this numerical example? Because very clearly with the numeric example, that's actually not what's happening, right? Because traditionally we do that. But when you start adding all the numbers up until double that number, like when you add up into, like look what's happening with the terms, right? How many terms are we actually adding each time? If I start with 1, right, and go to 2, now I'm adding 2 more terms after that. These 2 here are introduced. And then if I start from 4, I'm adding 2 more terms afterwards. And if I start from 6, I'm adding 2 more terms after that, right? So in this particular induction question, we're introducing 2 new terms, but this is saying if you're substituting all of this in, you're actually introducing only 1 new term, which is clearly not the case. Okay? So you have to be very careful when doing this. It's very easy to be mechanical about the process, but you have to consider, right, at the heart, what is the question asking? You're adding all the numbers from a particular number until double that number. Right? That's what we're doing here. So let's start again.
Yeah, let's start again.
And let's have a think, right? I'm actually going to do this question without having to rearrange this part. The way I'm going to do it is I'm going to say, all right, if I'm adding all the numbers until k plus 1 and to double that, that's obviously like double k plus 1 is just 2k plus 2. Would you agree? You can expand that out. My question is though, what's the term before this? Yeah, what do you think?
Oh man, I was going to say 2k plus 1.
2k plus 1, because what's the previous term? You just take 1 off. That still works, right? So because here, right, you go up to double it, and then if you just want 1 term before, well, that's just you take 1 off, and then can you see that this is your 2k now because that's where the old series stopped. Can you see that? Can you see that it goes from 3 to 6, and then when you take the next n value, right, it goes up until 6, which is your 2k, and you add in 2 additional terms. Can you guys see that? Does that make sense? So the term before this now is 2k. Right? And you should be able to see what's going on here now, right? This explains the extra 2 terms going on. We have 2k plus 1 and 2k plus 2. We still haven't actually solved the problem of a missing k over here, though. Yep.
Well, we actually had 2k plus 1.
Yeah, where did that come from?
But the thing is, well, we had it because we realised that that was the one before, but then we had that extra one on top of it, which made it wrong. But we thought the thing making it wrong was 2k plus 1.
We also had...
There's feels in there. Get that down for me. Now, you can actually, I haven't tried doing this with a rearrangement, but you probably could, but I want to show you a way to do it without rearranging, okay? The way I'm going to do it without rearranging is, if you just want to introduce a k to the front, remember these additions, they're commutative, which is a fancy way of saying the order doesn't really matter, right? Like I've kind of drawn these brackets here, they don't really need to be here, right? But what we can do is we can recognize that, like, we can just kind of take one of these k's from over here, can't we, right? I can just say, okay, if this is what I'm looking for, and I need a plus k over on this side, right, I can just kind of take one of these guys. I could split them up, right? I can say, all right, thank you. I'm going to borrow one of you, and you go over here. Can you see how that doesn't change anything, right? Like 2 lots of k, you can break up into k plus k, and I'll just move on over there, right? I'm allowed to do that, yeah. What that does now is that this guy over here, that can just stay by itself, but this whole summation will just end up in this, right? So this will be
Oh, there's an extra k.
3k, k plus 1 on 2,
You just have to move the k back.
plus, yeah, we just moved the k back.
Isn't that the same as minusing k?
I guess it would be, yeah.
Lit fam.
That's fine too, you can do that as well. And then this would become, what's this going to be here? 3k plus 3, right?
Okay, what's the second trap?
From step 2. Who said there was a second trap?
I did. Because I have, like, we have that.
Yeah? You have this?
It doesn't work.
It doesn't work. I suppose the question is now this is where it becomes a more natural kind of induction question. How do we rearrange this so that it becomes this? And my first thought is that I'm thinking, this is under a common denominator, this one isn't. So why don't we do that first, right? That's what I'm thinking first. So what's the best way to put this under a common denominator? Okay, so we can multiply top and bottom by 2 here. Still looking a bit messy. What can we do to tidy it up? Expand, yeah?
Is there a better way? Oh, factorize.
Why don't you guys try?
Expand just out of the like terms.
Yeah, go try. So, as in why do I do k plus 1 for all of them, kind of?
Yeah.
Yeah. Well, because what you're saying here is, like, when you let n equals to k plus 1, you're replacing all of these with k plus 1.
Oh, we don't do that usually.
Well, that's because in the usual induction questions, there are no n's here. It's usually just, look at the one I gave you, it's like n plus, what is it? It's 1 plus 4 plus 9 plus all the way until n squared. So the only one you're replacing is n squared at the end. Right, whereas this one's special because the n's appear throughout the whole series. That's
So, like,
very different.
All of them, just when you get to separate all of them again.
Well, that's actually what you're saying when you do this. When you let n equals to k plus 1, anytime you see n, you're replacing with k plus 1. It's just usually, we're not used to seeing n's throughout here. So it's kind of an oversight. We just don't include it, right? That's why this question was so tricky, because the questions don't usually do that. Yeah. It's a good question. You got something for us, Matt?
Yeah, that's been done.
You done it. And what method did you try to use?
What do you mean? Oh, we just factorize.
Okay. And this is kind of a, I suppose, running thing throughout these kind of problems, right? Do you expand things or do you try and factorize them? I guess the advice is to use whatever works best for you. But in general, if you expand things, you are probably creating more work for yourself. You can still get the same answer, but if you expand things, you're probably going to end up having to factorize anyway, is probably what's going to end up happening. You can actually save yourself the work, and you can actually factorize from this step. How can you do it? Well, what I'm thinking is I see that there's a k plus 1. I can see there's a k plus 1 here. I guess the question is, where do you get a k plus 1 from here? Well, in actuality, you can factorize the 3 out from here, right? Can you see that? So you get 3k outside of k plus 1. And I guess we're putting this under a common denominator, aren't we? And then we can factorize out the 3 from here. So what's this going to become? 6, yeah, because it's a multiplication. So just be careful, that's 2 times 3. That's 6 outside of k plus 1. And this is all over 2 now, right? And let's just go back over here. And then we can say, well, all right, k plus 1, they're in common from both of those terms. So we factorize that out, and we get 3k plus 6 all on 2. And that's just a nice little factorization again. We get 3 outside of k plus 1, k plus 2, all on 2, which is the right-hand side. And therefore, nice little conclusion, just like we do in English, right? And I suppose that's how we have harder mathematical induction, right? The questions that they give you are not in their usual kind of context, right? We have a question that's incorporated n's throughout the whole summation, which means that we have to replace that throughout all of these when we do the n equals k plus 1 substitution. And also, it was a bit trickier with the shifting series. That thing was very, that can throw a lot of people off as well.